Good evening, everyone. Just want to get a quick jump on tomorrow's lecture. Wanted to run through a quick tutorial on calculating effect sizes within these one-way repeated measures designs, just so that we don't have to spend time doing this tomorrow. And you have a quick tutorial. It's pretty easy and straightforward. Just want to go through these couple slides this evening. If you remember, we had for just this very simple one-way repeated measures ANOVA design, we've got two different data sets that we're using. One involves a set of ordered means where we're looking at reductions in depression scores among psychiatric inpatients over the course of a 6-week period. So we have here, there's a cursor, scores at intake, scores at 2 weeks post-intake, 4 weeks, 6 weeks. And so remember, in this case, we can't just scramble around these repeated measures and have them make sense. They're coming in a sequential order across time. We also looked at a data set where we're looking at people's willingness to maintain friendship with some hypothetical victim of some sort of life stress. Here we have a series of 8 different vignettes that people are going through and responding to the extent to which they'd be willing to provide support or friendship to these individuals. Now with this one, these, and actually in this study, remember we talked about these being completely randomized across individuals. So the order doesn't matter. It doesn't matter, again, which one of these means we model first. The repeated measure factor here doesn't have any natural order, and so we could flip things around. And so again, we'll be working with these two handouts that were posted on the course website. So we went through and found, remember, as we looked at these, if we're looking at the ordered means, again, looking at our repeated measures factor here, we're seeing statistically reliable effects on our repeated measure here, regardless of what corrected statistic we're using. And so we would conclude that at least one of those treatment means are different than the other based on this omnibus effect. And if we go down through and take a look, we can obviously see clear reductions in symptoms over the course of time, which is what we would hope within the context of a treatment. So this is sort of demonstrating what's going on with that repeated measures effect there. Same thing within our vignette study, also seeing a significant omnibus effect of our repeated measure, our within subject factor here, which is our friendship rating. Again, so we would conclude based on this omnibus effect that we have a reliable difference across these means somewhere, right? And if we take a look, we see that these are kind of all over the place, but again, wanting to make sure we were taking a look at the scale here, seeing that we've got very slight differences, but between the repeated measures design and the relatively large sample of 231 that we have here, lots of power to detect differences across ratings. Okay, so want to go through and make a quick note on looking at calculating an omnibus effect size within the context of repeated measures designs. So again, eta squared, this is, if you recall from our between subjects lectures last semester, eta squared providing an index of the proportion of total variability attributable to an effect. So here, calculation of eta squared being our sum squared for effect, whatever effect that is we're looking at, over the total sums of squares for the entire design. So eta squared is nice because it's easy to interpret. It's kind of like an R squared, right? So this is the proportion of variability in our outcome that's attributable to differences in vignettes or differences in ratings across time if we're looking at our ordered example. Okay. Problem is that our eta squared is sensitive to sort of the type of design that we're running. As we start to have multiple effects within the design, we're going to have, for example, a 2x2 ANOVA. We've got a sum of squares effect for factor A, factor B, and then the interaction. And what ends up happening is we end up, if we want to take a look at, let's say we have a significant effect for factor A, a significant effect for factor B, and then the interaction is also significant. What we're doing here is we're taking a look at each one of these individual effects and taking it over the total variability in the design. And so what ends up happening is we're counting all of these effects, even though we are counting for systematic variability in the outcome. All of the other effects that we're getting is calculated here in the total. And so what we might end up doing is underestimating the magnitude of our omnibus effect. It's going to be smaller. It's going to tend to be, our eta squared is going to tend to be smaller the larger our designs end up being. Now this is particularly true if you have less of an issue, if you have an orthogonal design where everybody's randomized to different conditions, but as you start to get relations between some of your factors, particularly if they're unobserved variable, or non-manipulated pre-existing individual difference variables, will start to get smaller here. So eta squared, something we can calculate, advantageous in terms of straight interpretation, but some problems in terms of providing a good index of effect. Our partial eta squared, again, if you recall, provides an index of the effect relative to unexplained variance here. So in the calculation of our partial eta squared, we're taking the sum of squares effect over the sum of squares effect plus the error, the stuff that we're not explaining, any other systematic effect. Again, if we're thinking about a 2x2 ANOVA design within the context of, say, a between subject study, if we have three effects, one for factor A, one for factor B, and then the interaction, and we're trying to calculate eta squared or partial eta squared for factor A, we're just looking at the sum of squares for factor A over the sum of squares for factor A plus whatever our error term is here. So we're ignoring everything except for our effective interest and then whatever unexplained error that we have in the model. What we're doing is we're capitalizing on other effects as controls, shrinking down that error term so that we don't end up underestimating our effect with our partial eta squared. And so basically what we're doing is with our partial eta squared, looking at this as proportion of unexplained variance that's being attributable to whatever our factor. Okay, but what ends up happening, and partial eta squared is fine, although we still have problems with partial eta squared being an overestimate of our population effect. Remember, that's why we start calculating omega squared and partial omega squared. But in general, our partial eta squared starts to become problematic for our repeated measure designs because we end up with multiple sources of error within our repeated measures designs. Remember that what we have is we have a sum of squares error term that's associated with our repeated measure, and then a sum of squares that's associated with our between subjects factor, or our sum of squares between that sucks out all that individual difference. But when we're calculating partial eta squares, what we're doing is we're ignoring that. Okay, and so what ends up happening is our concern is that our partial eta squared is going to be too high when we've basically sort of not counted any of the between subjects error within the context of this effect size. Okay, so if we go, for example, to illustrate this, if you recall, so for our zoom this up here. So for our ordered means, so we have here our sum of squares for our effect. This is what's variability that's being accounted for by differences across assessment point. Okay, and then this is the rest of our within subjects error that's not being accounted for. But then remember, we also have down here our between subjects effect, and this is where this our sum of squares error here, this is all the variability that's attributable to individual differences that's being sucked out. If we're calculating partial eta squared for our repeated measure effect here, this 5.25, basically we're taking this term, 69,586 divided by 69,586 plus our error term here, and this is going to give us our partial eta squared. And so basically this is saying our repeated measure is accounting for over 50% of the variability, but that's just within our repeated measure. We've sort of ignored all the stuff that's chalked up to our between subjects. That's still error. We haven't necessarily accounted for it. We're just saying that that's due to individual differences. And so the concern is with partial eta squared, what we end up doing is inflating our measure of effect because we're not taking this between subjects error into account. Okay. And again, you can verify this on your own. If you go through and take this divided by the sum of squares assessed plus the sum of squares error for your repeated measure, you're going to get your partial eta squared right there. Okay. So what we can do then is we can go through and we can calculate what's known as generalized eta squared. Generalized eta squared developed to look at the proportion of variability accounted for by our effect relative to all sources of unexplained variance in our design. This is probably a little bit more fair, right? We're not cherry picking which error terms we want to look at. We're going to go through, calculate all of this. Now, this is something that's not provided for you by SPSS, and part of that is because the calculation of generalized eta squared is going to depend on what effect you're looking at and sort of the size and characteristics of your design. And you'll see that Bakeman article that I'm having you all read and work through that's probably frustrating you right now, but this will give you a sense for where we're pulling some of these error terms off, at least in the case of a one-way design. So specific formula for generalized eta squared for our one-way repeated measures ANOVA is going to be sum of squares of our repeated measures plus the sum of squares for our repeated measures plus the sum of squares error, which is what we would get for our for our partial eta squared. But here we're going to add in our between subjects designs, or between subjects error as well. Okay, so in this case, we've got our sum of squares for our repeated measure over all of our unexplained variance. So we've got our between subjects error, our within subjects error, and so calculation of generalized eta squared for ordered means, we would take our sum of squares within, so our sum of squares for our effect, plus sum of squares for our within, divided our sum of squares within divided by sum of squares within, plus the sum of squares error for our repeated measures, plus the sum of squares error for our between subjects effects. Okay, and if we go through and we were to calculate that, we would take for generalized eta squared, we take our within over our within plus our between plus our sum of squares error for our repeated measure. We're going to get a generalized eta squared of 0.263 in this case, which you'll notice is substantially smaller than your partial eta squared. But this makes sense because what we're doing is we're basically doubling your error term by the denominator here by taking into account error attributable to individual differences within the context of this one-way ANOVA. Okay. Same thing for our unordered means here. I'll sort of zoom in here so you can see. We would take, so our partial eta squared tells us we're accounting for about 8% of the variability within our repeated measures variability here. And so this would be 81.79 divided by 81.79 plus 902.7. This is going to give us your partial eta squared. If we wanted to calculate our generalized eta squared, again for this one-way repeated measure design, we would take our within over the top of our within plus our within subjects error plus our error between subjects, our individual differences error there, and this is going to give us a generalized eta square of 0.038. Okay. And so again, we'll notice that this is going to be considerably smaller than our partial eta squared, again, because we're taking all the unexplained variance into account. Now, in general, what ends up happening is partial eta squared ends up being larger than generalized eta squared, which ends up being larger than our eta squared. But if you notice, and are sort of keyed in on this, you'll notice that in the one-way case, our generalized eta squared is actually going to be equal to our eta squared. Because remember, eta squared is the sum of squares of effect over sum of squares total. When we take a look at the one-way repeated measures case, our sum of squares repeated measure plus our repeated measure plus our between plus our within, this is the total. There's no more variability that we've chopped up here. And so the one-way repeated measure ANOVA is a special case where our eta squared is going to be equal to our generalized eta squared. But as we start to add additional within between subjects factors within this, what we'll see is our generalized eta squared will tend to be larger than our eta squared. Okay, so again, generalized eta squared, this is nice across a range of we can use this across a range of designs. Generally should be preferred, but what you'll need to do is you're going through and calculating this, making sure that you're using a formula that's consistent with the type of design that you're using for your study. And so this will start to depend on whether or not you're looking at between subjects factors or within subjects factors, and how many of those that you're looking at. And when we get in the weeds with this, changing things around, if your factors are pre-existing factors or unmanipulated factors, or if they're experimentally manipulated factors, going to start to impact how you go through and calculate that. But you all are champions, and I'm going to let you work through that on your own. So that pretty much does it for working through our repeated measures effects. So go through, take a look, calculate those on your own, but that should save us some time tomorrow so we can jump right into follow-up tests with this. So hope this is helpful, and let me know if you have any questions. All right.